Imagine waking up tomorrow and discovering that Apple can no longer build new iPhones. Nvidia can't make new AI chips. TSMC's factories suddenly stop producing the world's most advanced semiconductors. Intel's roadmap falls apart. Artificial intelligence slows down. Data centers stop expanding, and governments around the world begin holding emergency meetings. Not because of a war, not because of a financial crisis, but because one company disappeared. A company most people have never heard of. A company located in a quiet town in the Netherlands. A company that builds a machine so complex, so difficult to manufacture, that no competitor has successfully replicated it. And without that machine, the modern digital world simply cannot move forward. This is the story of ASML. Every era has its hidden giants. The industrial age had steel, the electrical age had the power grid, and the digital age, it has a machine that prints the tiny patterns that become the processors inside your phone, your laptop, your car, and the AI systems that are reshaping civilization. For years, ASML operated quietly in the background. No flashy products, no famous founder, no billion users. Yet today, some of the largest companies on Earth depend on technology that only ASML can provide. And the strangest part? There was a time when many people believed this company was chasing an impossible dream. Chapter 1. The company. ASML was founded in 1984 as a joint venture with the Dutch electronics company Philips. Its early headquarters were hardly glamorous. Engineers worked in modest buildings, far away from Silicon Valley and the spotlight of the tech industry. At the time, the semiconductor world was dominated by larger players. Japanese companies like Nikon and Canon were major forces in lithography, the process used to print circuits onto silicon wafers. ASML wasn't expected to become the winner. It was the outsider. And for years, it behaved like one. Instead of trying to dominate immediately, the company focused on solving increasingly difficult engineering problems. Slowly, it improved its machines. Slowly, it gained customers. And slowly, it earned something even more valuable than market share: trust. By the 1990s, chip makers were beginning to realize that making transistors smaller would require dramatically better lithography technology. The industry faced a terrifying challenge. The laws of physics were starting to push back. As transistors shrank, traditional manufacturing methods became less effective. Printing the next generation of chips would require using light in ways that had never been done before. And that's when ASML made the decision that changed everything. It bet the future of the company on a technology called extreme ultraviolet lithography, EUV, a technology so difficult that many experts weren't sure it would ever work. Chapter 2. The 20-year gamble. Most companies spend a few years developing a new product. SML spent decades. The company invested billions of dollars into EUV research. Years passed, then more years passed. The technology still wasn't ready. The light source was unstable. The optics were incredibly difficult to manufacture. The entire system required levels of precision that sounded almost absurd. At one point, even people inside the company wondered whether the project would succeed. ASML's executives later admitted that the company had placed nearly all of its chips on a single bet. If EUV failed, the consequences would be devastating. But something remarkable happened. Instead of abandoning the project, some of the biggest companies in the semiconductor industry decided to support it. Intel invested. Samsung invested, TSMC invested. Competitors in the marketplace became partners in a shared mission. That alone tells you how important the technology was. These companies weren't funding a science experiment, they were funding the future of computing. And after more than 20 years of development, SML finally proved that EUV could work in commercial manufacturing. It was one of the greatest engineering victories in modern history. But to understand why, we need to see how the machine actually works. And that's where the story gets weird, really weird. Chapter 3, Building the Impossible Machine. Imagine trying to draw a pattern so small that it's thousands of times thinner than a human hair. Now imagine doing it millions of times, every single day, with near perfect accuracy. That's essentially what ASML's EUV machine does. The process begins with tiny droplets of molten tin. Each droplet is fired through a vacuum chamber at incredible speed. Then a powerful laser strikes the droplet, not once, twice. The second pulse turns the tin into a plasma that becomes hotter than the surface of the sun. For a brief moment, that plasma emits extreme ultraviolet light with a wavelength of just 13.5 nanometers. And here's the problem. This light is so difficult to work with that it gets absorbed by almost everything. Air absorbs it. Most materials absorb it. Even ordinary lenses are useless. So ASML had to build the entire system inside a near-perfect vacuum and guide the light using mirrors instead of lenses. Those mirrors are manufactured by the German company Zeiss. They are often described as the flattest surfaces humans have ever created. If one of those mirrors were enlarged to the size of a country, its tallest imperfection would be smaller than a tiny bump in the road. Only with that level of perfection can the light be directed onto a silicon wafer and print the microscopic blueprint of a modern chip. The result is a machine weighing more than 180 tons, containing hundreds of thousands of parts, and costing well over $200 million. Some people call it the most complicated machine humanity has ever built. And honestly, they may have a point. At this point, ASML had accomplished something extraordinary. It had turned an impossible idea into a working machine. But building the machine was only half the battle. Because the real question was no longer, can EUV be built? The real question was, can anyone else build it? And as the world would soon discover, the answer might be no. Chapter 4. Why nobody can copy ASML. By now, you might be wondering something. If ASML's machines are so valuable, why doesn't someone simply build a better one? After all, Apple competes with Samsung. Microsoft competes with Google. Nvidia competes with AMD. Competition drives innovation. So, where is ASML's competitor? The answer is surprisingly simple. No single company knows how to build the machine, not even ASML. That may sound strange, but it's true. An EUV lithography system isn't the product of one company, it's the result of thousands. More than 5,000 suppliers contribute components to every machine. Some build lasers, others manufacture vacuum systems. Some specialize in motion control. Others produce materials measured in atoms. And then there's Zeiss. If ASML is the brain, Zeiss is the eyes. The mirrors inside an EUV machine are unlike anything else on Earth. They're polished so perfectly that even the smallest imperfection would ruin the entire process. Imagine shining a flashlight at a wrinkled mirror. The reflection scatters everywhere. Now imagine trying to guide light that's invisible, using mirrors that must be perfect down to fractions of a nanometer. That's what Zeiss had to solve, and it took decades. The relationship between ASML and Zeiss became so important that ASML invested billions of dollars into Zeiss itself. Not because it wanted to own the company, but because it couldn't risk losing access to the technology. This wasn't just a supplier anymore. It had become part of the foundation. And that's what makes ASML almost impossible to replace. It's not one invention, it's thousands. It's not one patent, it's decades of accumulated knowledge. It's not one factory, it's an ecosystem built over 40 years. Even if another perhaps the most fascinating part of this story is that ASML isn't slowing down. Because while the world is still trying to catch up with today's technology, its engineers are already building tomorrow's. Next, we'll look at the future of ASML, the next generation of machines, high-NA lithography, and why the future of artificial intelligence may depend on technology that doesn't even exist at scale yet. Chapter 6: Building the Future. For decades, ASML was trying to build a machine that many believed was impossible. Today, that machine already exists, but the company isn't celebrating, because the next challenge is already here: artificial intelligence. Every new AI model demands more computing power than the last. Companies aren't just competing to build smarter software anymore, they're competing to build more powerful chips, and those chips require even greater precision. That's where ASML's newest breakthrough comes in. It's called high-NA EUV. At first glance, it looks similar to the previous generation, but inside, almost everything has changed. The optics are larger. The mirrors are even more precise. The numerical aperture, the angle used to focus light, has increased dramatically, which means manufacturers can print even smaller features onto silicon. Smaller transistors, more computing power, lower energy consumption, and faster artificial intelligence. Each high-NA machine costs well over $350 million. It weighs hundreds of tons, requires months to assemble, and demands some of the most advanced engineering ever achieved. Only a handful of companies on Earth can even afford one: Intel, TSMC, Samsung. The race has already begun. While the world debates the future of AI, ASML is quietly building the machines that will make that future possible. And they aren't stopping there. Engineers are already researching technologies beyond high-NA, the next generation, even smaller, even faster, even more precise. Once again, they're attempting something many people believe can't be done. History suggests betting against ASML isn't a very good idea. It's easy to admire companies like Apple or Nvidia or Google. They're everywhere. Their products are in our hands, our homes, our daily lives. ASML is different. Most people will never own one of its products. They'll never visit one of its factories. Many won't even hear its name. And yet, every time you unlock your smartphone, every time an AI answers your question, every time a self-driving car processes the road ahead, there's a good chance ASML helped make it possible, not by building the device, but by building the machine that built the chip that powers the device. Sometimes the most powerful companies in the world aren't the ones standing in the spotlight. They're the ones quietly working behind the curtain, changing history, one breakthrough at a time. And perhaps that's the greatest lesson of all. Power doesn't always belong to the company everyone knows. Sometimes it belongs to the company everyone depends on. If you enjoyed this documentary, consider subscribing to Foundry. Every week, we explore the hidden stories behind the world's biggest companies, the technology shaping our future, and the decisions that changed everything. Until next time, thanks for watching.